Bismillah ar-Rahman ar-Rahim. We are going to talk today about heat capacity and latent heat. Of course, we know whenever we apply heat to a subject, its temperature increases and vice versa. The most important two items in heat definitions, we have what we call specific heat capacity. It's the amount of heat to raise the temperature of 1 kilogram of a substance by 1 Kelvin. The systemic industrial system, items of this unit is joule for kilogram for 1 Kelvin. Of course, as we know that 1 Kelvin is commensurate with 1 Celsius. We always use Celsius. This is specific heat. Whenever I come to heat capacity, the total heat required to increase the substance, whether it's 3 kilo, 2 kilos. So I simply multiply the specific heat with the weight. The items of the unit are only two, joule and Kelvin, because the kilogram is being added. See, so the first one has 3 items in its unit, and the second, which is heat capacity, has only 2 parts in its unit. Now, whenever we come to know the specific heat of the human being, it's around 3.5 kilogram. I'm sorry, kilojoule. Now we are beginning to talk about the kilojoule for each kilogram, for each Celsius. You see, 3 items representing the specific heat. So whenever I have a patient with a 70 kilograms weight, I multiply by 700. As we can see, it reaches around 245. It's not important to memorize, but it's the most important to know the specific heat of the human beings is 3.5 kilojoule. What's the importance of that? The total heat of the human being is around 80 watt. Watt, you know that watt is joule per second. Joule per second. So we are going to make it easy that the heat of a human being, normal human being, 70 kilos, around 80 watts. It's easy to memorize. So suppose the patient is subjected to a temperature of 36. So we have a decrease in 1 degree. How much heat we are required to increase the temperature from 36 to 37? As we know before, that the total heat capacity of the human being is around 245. In this point, this 1 degree, we need an extra of 14.4 kilojoule per minute. Per minute, the patient must shiver. This is the only way to gain temperature, by shivering. So this amount of heat in minute takes around 17 minutes so that we can increase the temperature from 36 to 37. Simply speaking, knowing the specific heat of the human being, knowing the amount of temperature the patient is being decreased, we can figure out the time that would take for this temperature of the human being to increase. The total, we say the total body heat content equals the product of the mean temperature of the patient times the heat capacity. Now we come to the specific heat of water. Water is very important as regarding liquid in anesthesia. We will talk about later on. We can see from the figure that we have 2 pots. One of the pots, each of them contains 1 kilogram of water, which equals 1 liter of water. And we have the temperature of X. We want to increase it to X times 1, or plus 1, I'm sorry. So I want to elevate this amount of water 1 degree. How much I will need of heat to elevate this temperature by 1 degree? It's around 4.18 kilojoule. This is a figure you must remember. because it is the specific heat of water. Water is has the greatest specific heat among liquids. And this figure, maybe it reminds you with the 4.28 of the wave micrometer of wave of infrared regarding CO2 absorption. Maybe we are trying to memorize. So whenever I have a pot and I want to increase this water degree, in addition, I support with 4 or 4.18 kilojoule. We are talking about a kilojoule. This 4.18 joule is equals to 1 calorie. Calorie, you have a small liter. Whenever it's a kilocalorie, we substitute this small letter with a capital C. The people working in diet, they always use the capital C representing kilocalories. You see, of course, water being the most which has the most high specific heat, we can use it, of course, in the hemovaporizer to make the temperature steady all over the procedure, so that will keep the vapor pressure. Now, as a simple application of the specific heat, suppose I have a 2 kilogram of blood, which equals mostly 2 liters of blood. I want to heat it so that I can give it to the patient. Suppose the temperature of the blood is 5, and I want to make it reach to 35. Knowing the specific heat, as we can see, of blood, which is less than water. Simply, you don't have to memorize it, but water, you must memorize the specific heat of water. So whenever I am multiply the specific heat in the amount of blood and the difference in the temperature required, I can get the total heat required to elevate this amount of blood to be 35 degrees Celsius, so that I can admit it to the patient. The most nice thing about latent or the specific heat of gas, that's very low. It's very low. In kilograms, of course, we always represent gases or by volume, not by kilogram. However, the specific heat of 1 kilo of air is 1.01 kilojoule for each kilo for each degree Celsius. 3 items representing the unit of specific heat. You see, so whenever we use gas, we always subject it or transfer it to a volume, so that it will be actually 1.2 liter or joule for every liter for every degree Celsius. 3 items. So the kilogram 1.01 is being substituted by 1.2 to shift from kilogram to joule. So it's around 1/1000th of the figure of considering a kilogram as a specific heat. The importance of that whenever you have a very low specific heat, the subject gains heat rapidly and loses rapidly, so that whenever I inhale a very cold gases, once it reaches the trachea, it loses its heat speedily. Because why? Because the specific heat of gas is very, very low. The point also in anesthesia, the cold dry gases that being inhaled by the patient is also being decreased in its temperature whenever it reaches the upper airway and the trachea. Of course, we can figure it out knowing the volume of air being inspired by multiplying the volume in the specific heat of gas. Now we're going to consider it as a volume. As we said before, it's 1.2 joule for each liter. Time the difference of temperature between the gas when before entering the human being and the required heat to reach the human being. So the difference between the 20, which is the ambient temperature, and the 34 degrees Celsius in the human being, it's 14. This difference is being multiplied by the volume and the specific heat, so to gain the amount of heat required to heat this amount of gas, which is very low. It's around 2 watts. As we said before, watt is 1 joule per second, 1 joule per second, you see? So it is a minimal amount of heat loss comparing it with the total heat of the human being, which we said before, it's around 80 watt. You must memorize this 80 watt. Now we come to the latent heat. Latent heat means that it is a heat required to change the subject from something to another state. We have what we call latent heat of vaporization, which is very important in anesthesia. We have latent heat of fusion or melting. A solid is being transferred to a liquid, and then we have latent heat of condensation whenever the vapor turns to water, and then lastly, the latent heat of crystallization. A liquid is being shifted to a solid. We have also specific heat, latent heat. We have a specific latent heat. It's the amount of heat required to convert 1 kilogram of a substance from one phase to another at the given temperature. This is why the units of this or the items of this unit is only 2, because the temperature has not changed. So the unit is represented by joule for each kilogram. And we can see from the figure that we have 1 kilogram of water at a temperature of 100. We want this 1 kilogram to be vapor, 1 kilogram vapor at the same temperature. How much would we need of heat to shift this or to create this situation? We only need 2.26 megajoule. Now we are coming about the mega. We began by joule and the kilo and the mega. You see, so this is the amount required whenever I want to make the liquid the liquid of water at 100 degrees Celsius becoming vapor. Now another point: if this water, the 1 kilogram at 37, and I want to shift it to a vapor, I will need definitely more heat in the figure of 2.42. The last one was 2.something 20s, and now we have 2.42 megajoule to shift or to change this liquid to vapor at the same temperature. What are the items of this unit? Is only 2 items, because the temperature has not changed much. Of course, as we know that nitrous oxide, the critical temperature is 36.5. What does it mean? That means at 36.5 of nitrous oxide, this liquid spontaneously is being transferred to being a vapor without any need of heat. So how much is the latent heat required for nitrous oxide to be shifted from liquid to vapor at 36.0? Of course, it be 0, simply speaking. What's the importance of latent heat in anesthesia? As we said, the latent heat of vaporization of liquid anesthetics needs heat. It takes this heat from the liquid and from the surroundings, so that it will affect the final process of vaporization and the final vapor pressure, which is required to induce anesthesia. But of course, as we know, in all vaporizers, there are compensation to maintain the vapor pressure at different temperatures. As you can see from the figure above the graph, this is called a graph, the relationship between temperature and latent heat. We can see whenever the temperature is increased, differently the latent heat required to shift from liquid to vapor will decrease. On the other hand, this figure also shows the nitrous oxide. whenever nitrous oxide reaches 36.5 degrees, it doesn't need much heat to be shifted to a vapor. So we can say that the latent heat of nitrous oxide at this temperature is 0. Now we are talking about design of vaporizer, how to keep the concentration of vaporizers. Now, and it's nice to know whenever I want to, of course, as we see, the temperature of the liquid vaporizer is 50 and the ambient pressure of 20. It has to be very cold, so the vapor pressure will decrease. So we must have compensation, and this is the graph on the right side that correlates the temperature to the saturated vapor pressure. As you can see, that the saturated vapor pressure, of course, as we know, is temperature dependent. Nitrous oxide, whenever I empty the nitrous oxide very speedily, in a way, the pressure will decrease. The pressure will decrease. So whenever I close this cylinder again, the pressure can be increased. What's the importance of this? The cooling effect of such speedy outcome of nitrous oxide will cause a freezing of on the outlet of the cylinder, and will obstruct the flow of the cylinder. As we have seen from this graph, that at a speedy flow of 5 liters per minute of nitrous oxide, we find that the dots appeared by time above. This makes the difference. You see, whenever I close, the pressure regains its own way. So that we must open the nitrous oxide slowly, so that the pressure can be restored. Of course, we know carbon dioxide and cyclopropane are in a liquid formula, and we don't have much to be affected by the cooling. It's not much affected. Now is the important thing that the critical temperature of nitrous of oxygen is around -119 degree. Of course, we're going to talk about the oxygen cylinder. Oxygen cylinder, as we can see, is made of a gigantic flask. This is important. The space between the two layers is capable to keep the temperature very low, and we find that the temperature of this flask is around 5 bar. What happens? And then the temperature of this flask is around -160 degrees Celsius. What happens? The nitrous oxide is being transferred from liquid to vapor, and then it comes out very cold. So we must have a coil of superheating instrument. Suppose this oxygen coming out from the cylinder, which was 7 bar, in the pipe system will reach 4.1, as most gases entering this pipe system. We have in addition what we call a pressure rising vaporizer in case that there is too much flow of oxygen from the cylinder, which is in need of more latent heat, will decrease the temperature, and so that the vapor pressure will also decrease, because as we know, the vapor pressure is temperature dependent. So a pressure raising vaporizer is sensed by a valve. Whenever the pressure is decreased, as a regard of this taking oxygen too much, it will compensate by taking liquid and causing vaporization, so that it will go with the part coming up from the top of the cylinder to keep the pressure of the flask, so that the saturated vapor pressure will be kept. Whenever I leave the cylinders for a long time closed, the pressure of it increases, so that there is a safety valve to release this pressure. As we said before, latent heat the heat required to heat the cold gases reaching the human being, it's around 10 joule from the 2 watt from the 90 watt of the human being. Now, the most important point that we require also the dry gases to be humidified. This normally occurs in the human being because, of course, humidified gases soothes the upper airway. It decreases the temperature, as we will see now. So whenever I have 7 liters of flowing gas to the human being, and this 7 liters is required to have 34 milligrams per liter, as we said before, the amount of water in a contained gas. It could be milligram per liter or gram per cubic meter. So we have 7 liters of gases must be humidified by amount, how much? By 34 milligram liter per second. I'm sorry, 34 milligram per liter. All this will totally reach to the figure you can see from the page. This amount of water must be taken off from the mucous membrane of the tissue. How can we figure out the amount of heat required to vaporize the water of the tissue? We can know that the specific heat of vaporization at 37 is 2.42. I'm sorry, this is at 2.5. I'm sorry. Multiply that about the amount in kilogram of the liquid required to humidify this amount. We'll reach the end result that for 7 liters to reach the human being, it requires around 9.6 watt of heat, so that we have the 2 watts to increase the temperature of water of the air, plus we have around 10 watt to humidify these gases. You see, this figure is much more than what happens in the anesthesia, because anesthetics gases are more dry and so forth. The importance of using this humidification process, it will affect the temperature of the human being, especially in young children, causing hypothermia. This is why we must use humidifiers with anesthetic apparatus. I hope that I did my best. It's an effort. I hope that I'll be rewarded from God from it, especially after my death. Wassalamu alaikum wa rahmatullah wa barakatuh.